So Viktor Smits, I recently became the head of the Dutch branch of Revolut. And what I'm going to talk to you about today is Pragma. It's actually not something that I worked on myself, but I think it's a very interesting development that we have seen so far at Revolut. The beginning will be maybe a bit technical, but don't worry, I'm not technical myself. I presented this to my wife, who's actually in regulatory compliance, and she fully understood it. So that's a very good sign. And then at the end, hopefully, I will talk to you about some practical implications that we've already seen. If I show you a simple sequence of words on the screen, I think most of you will be able to fill in the blanks, right? So I went to the bank and the ATM swallowed my card. And then I ordered a new one, probably through the online banking app or maybe on my phone. But if I would show you a sequence of banking transactions, that all of a sudden is much more difficult. And if we would feed this series of banking transactions into a classical large language model, it's going to really struggle with that because it's not made for amounts or values of banking transactions. But what we have seen is that natural language and banking events are actually very similar. So they are sequential, contextual. There's certain patterns. There's anomalies. Anomalies could be in language, it's a typo, but for us it might be fraud. So there's quite some consistencies between the two. And so we've been working at Revolut to develop a model that is very good at reading banking events. And the name of the model, that is called Pragma. But before talking about that, let's talk about the challenges that we face today. So when we build models today, let's say the fraud team wants to build a model. They will take a few data engineers in the business, they will put them in the room, they will spend a few weeks or months feature engineering all the features for the model, run it, train it, etc. And then when the credit team wants to do that, they will do the exact same thing. They will start feature engineering again, they iterate over all of this, come up with a model. So you've got very strong domain bottlenecks and slow iterations, duplication of efforts, the classical issues that we know today. And so there is an opportunity. The opportunity is a foundation model, and you might have already heard of it, but what does it actually mean for a bank? Well, it's a general purpose AI trained on a massive amount of data. And we don't tell the model what to do. We don't tell it what the task is. We just throw everything in there, and then the model will have to learn the patterns that underlie all the data. And then at the end, we can fine-tune it a little bit to do fraud-specific tasks or credit-specific tasks or anything else. So to visualize this once more, previously we had raw data. You do manual feature engineering, and out comes features for the fraud models, features for the credit models, features maybe for money laundering models. And for each new thing that you develop, you do this over and over again. And the foundation model approach is different. You take the raw data, you train one big model once, and then you can use it downstream in all the different tasks. And so to build this at Revolut, what we did was we took data from, obviously, transactions. We took events in the application, so if a customer went through a certain flow, we captured that. We looked at trading events and also communication events. So if we send emails or push notifications, did the client interact with that? That's the data that we looked at. We took data from 26 million clients, more than 100 countries, and so in total 24 billion different events that the model was trained on. So it's quite significant. I think it's slightly over 2 years of training data. Now, how do you feed complex banking data into an AI? Well, we use tokenization. I'm not going to dive too much into the details here, but essentially what you do is you take a transaction and you split it up in, for us, 3 different fields. The first thing is the key. So is it, what's the type? Is the type a card payment? Is it something else? What's the direction? Is the transaction coming in or out? The amount, for instance, we don't feed the model the exact amount. We don't tell it was a transaction of 14.99 euros. We tell it it's within that percentile bucket. So each event, we tokenize it so the model can work with it. then what we do here, the model uses a rather simple architecture. So on the top, what you see is the profile state encoder. Really simply put, it will take the background of the customer. What's the age of the customer? Where do they live? When did they create their account? Are they on a paid plan? Like all the static details of the user. And at the bottom, we will feed it with all the event data. Could be transactions, it's the more dynamic things. So we merge them together, and then we combine with what the user is with what the user is doing, and we create a single mathematical profile for each individual user. So then how do you train your model? There's no objective that you try to do. You're not telling it to do fraud detection. What we simply try to do is it has to detect patterns. So what we do, just like in natural language models, we drop 15% of the event, and then the model will try to fill in all these blanks. And you train it billions of times until it's really efficient at predicting these gaps. And once you have that model, all you have to do to make it useful for downstream tasks is to add what we call the LoRa. What you do is you take your model with all your parameters and you freeze 98, 99% of all the parameters, and you only retrain 1%. And that way you can do it, you can fine-tune it for very specific tasks. So it goes really, really quick if you want to turn your model into a fraud or a credit or any other type of model. And that's just the background of what we did. And I think the most interesting bit comes right now is what are the results? And what I'm showing you now are relative improvements compared to the models that we already built over the last couple of years. So these are the improvements compared to what the fraud team has been doing for the last 3, 4, 5 years. Purely that. How does Pragma compare to it? So let's start with external fraud detection. The Pragma model that we developed just in a few months, and we didn't teach anything about fraud, improved the recall by almost 65%. So we catch 2/3 more fraud than the old models. If we look at credit risk, at Revolut, we have quite a young population, so that's quite a thin file population without too much data on it. And just by deploying Pragma, we improved the efficiency of predicting the credit default risk by 130%. It doesn't just stop at risk, so we use this also for business implications. Let's look at communication engagement. Imagine a client starts a credit application, they go through, and then all of a sudden they drop in the flow. We can try to reactivate the customer with specific comms, with specific marketing or activation campaigns. And Pragma is 136% more efficient at predicting the right channel and the right communication to reactivate our customers. We can also use it for product recommendations, or we can use it to predict recurring transactions. So it's highly efficient at those things, but it's not efficient at everything. So one of the things where we noticed quite a significant decrease in performance was money laundering. And the reason that we identify for that is that money laundering is quite a relational topic. It's about networks of different people. And the Pragma model that we developed is very individualistic. It looks at one person in isolation. So these networks, it's not good at. And these results, I think, are quite promising. But I think the most important implication of this is the operational impact. So no more feature engineering. We go from weeks of feature engineering to no feature engineering. Very low maintenance. One model that we can work on for all the different downstreams. Minimal build. And that is where we see the opportunity. So this is just an example of a very practical implementation of AI for us. We're not yet using it for all the production reasons. So this mainly was a research test to see what we could do with the data that we had. If you want to use this for regulated activities, you would have to make some changes. right? The AI Act doesn't allow you to use the full black boxes. So we can use it for marketing and communication, but you can't yet use it for, let's say, your credit procedures. So it's a bit of a test to see what we can do. And we are really, really happy with the results. And we have published the entire paper online, so you can Google that, you can find it, you can see all the technicals in there. And I'm sure there's people much more technically skilled than I am to provide more context on that. I try to keep it very short. I'm sure you've heard plenty of AI already and might start getting a bit hungry. Is there any questions that I might take? Yes.
Hi. So this is beautiful, actually, what you built, also what you researched. I had a few questions. Maybe you could answer. One is around, because you've got so much of data you're working on to create different value props. How did you go about training the models? Because I can imagine labeling or something that is a massive amount of effort. So I'd like to hear more about the training, what challenges you faced, and you mentioned it wasn't in production, but how would you have approached like adoption of these different value propositions or use cases? Thanks, Dan.
Yeah. So we try to do pretty much no labeling. Everything goes through tokenization. So we spent quite some time on tokenization and understanding all the different keys that you might have and the buckets, but we didn't do anything specific on the on labeling tasks. So the data that we ingested, that was the way it is. We didn't want to touch it too much, risking to bias it or steer it in a certain way. So the approach for tokenization works for all the data types that we were using. Then the training method purely is the mass modeling. It's dropping out things 15% and running it over and over again. So it gets good at predicting all these tokens. Challenges, there's quite a few challenges. First, this isn't cheap, right? We partnered up with NVIDIA just to get some of the hardware to do all this. So it's not going to be cheap. It's going to cost you a few million every month just to run or set it up. But then again, once you start doing things at scale, that starts to make sense for us. That's certainly a challenge. And then again, data as well. It's just like in every company. It's quite dispersed in different teams. And I think at Revolut we have quite a mature data setup. But even then, it's complicated to interpret data correctly and then to make sure that you take the right one. Implementation of it, it's going to go gradually. I think we're going to fine-tune this a bit more, see what we can do, and then we'll have it run in parallel to existing models for probably a long time before we a standard approach on to see if it's still efficient or if there's any flaws to it.
Yeah, I have a question, very interesting, by the way. My question, I'm not sure if it's more for you or your wife, but when you train the models, how do you balance between deterministic models where you have the obligation to explain versus using the full power of generative AI for unknown pattern recognitions, etc.?
Yeah. Certainly for the regulated activities, we need to have some explainability. So there are techniques that we can use to look a bit more under the hood and see which features determine that. So as I said, credit applications, maybe even fraud detection, we might have to dive under the hood and adapt it a bit. But there's quite some different models that we have that absolutely don't require this. Or what you do is you take this as an input for a more deterministic model, as one of the submodels that you use, and that's also a way to go around that. But yeah, it's certainly a challenge, and for very critical things, you want to have some grasp of what's underlying it.
Yeah. Thank you.
Fascinating. Any other questions? Yeah.
So just to confirm, you have only one AI model and you use your own AI servers as well?
We developed this, of course, in parallel to everything that we have, so it's not widely implemented. This is just showcasing the possibilities that we have, but indeed, it's one model that we have, and then we fine-tune 1 or 2% of the parameters for specific tasks, and that is sufficient to get these results. If I think for this one we didn't do it on our own servers, but I think once we start going live, the idea is to do as much for ourselves. Yeah, data was anonymized to the largest extent to run this. Yeah.
Great. I will try to do my best. Please.
First of all, thank you very much. So the LoRa is only on the fine-tuning towards specific use cases. There was no use or need for other RLHF, like the human-based inputs to refine?
We didn't. There were a few options that we considered, but LoRa appeared to be the most efficient way to do it. Yeah.
Was there an experiment in that direction, just to see if it?
I would have to check, but it's in the paper, and I
Okay.
would advise to take a look. I know that our teams did look at a few different options, and that there's a good explanation on why we went with LoRa. But if I can send you the link afterwards, that might be the easiest. Thanks.
Amazing.
All right. Thank you.
Thank you so much, Viktor.